All right, let's dive into one of the most brilliant, unsung heroes inside your computer: memory management. It's the master illusionist that lets your machine juggle dozens of complex tasks, all within a tiny, finite space. I mean, really think about it. How is that even possible? You've got a massive game running, 50 browser tabs open, music playing, and somehow your computer just handles it. Well, it's not magic, but it's a series of incredibly clever tricks, and today we're going to break them down. You see, it all boils down to this one fundamental problem. You've got a fixed amount of physical RAM, those chips on your motherboard, but a practically endless desire to run more and more programs. And that's the central conflict that this whole story is about. So the first crack at solving this was pretty straightforward. But as often happens in the world of engineering, a simple solution created a whole new, really messy problem: a problem of wasted space.
The first idea, called contiguous allocation, made a ton of sense. When a program needs to run, the system just finds one single, continuous block of memory that's big enough to hold the entire thing. It's just like finding an empty shelf for a big book. Super simple, clean, and easy to keep track of.
But, okay, what happens when you're done with that program and you close it? Well, it leaves a hole. Then you open a new, smaller program, and it might fill part of that hole. And as you open and close stuff all day long, your memory isn't this neat set of shelves anymore. Nope, it becomes a mess of little, unused gaps scattered all over the place. And that mess has a name: fragmentation. This is the bad guy of our first chapter. It's when your memory gets so chopped up into tiny pieces that you can't start a large program, even if you technically have enough total free space. It's just not all in one big piece. And get this, it's not just one problem. There are actually two distinct types. So over on the left, we've got internal fragmentation. This is wasted space inside a block that's already been assigned. So imagine the system gives a program a 40 kilobyte space, but it only needs 32. That leftover 8 kilobytes? Just wasted. Then on the right, you have external fragmentation, and those are all the unusable little gaps between the allocated blocks. So the key takeaway is the difference. Internal is waste inside a reserved spot. External is waste between all the spots, and both of them are just absolute killers for efficiency. For a long, long time, this was a massive headache for anyone designing an operating system. So, how do you solve what seems like an unsolvable problem? Well, you stop playing by the old rules. You completely change the game. And that brings us to one of the most elegant and powerful ideas in all of computer science: paging. Paging just flips the old idea completely on its head. It asks a really simple question. Hey, wait a minute, why does a program need to be in one big continuous block of memory anyway? Instead, the operating system breaks the program into small, fixed-size chunks called pages, and it breaks the physical RAM into matching, same-size slots called frames. And this is the perfect way to think about it. Forget about finding a giant empty shelf for your huge encyclopedia. With paging, you basically tear the book into its individual pages. Then you can stick page 1 on the top shelf, page 2 on the bottom, page 3 way over in the middle. It just doesn't matter where they go. Okay, you're probably thinking, but how does the program not get totally confused? And that is the magic trick. You see, from the program's point of view, it still sees one perfect, continuous block of memory. We call this its virtual address. But whenever it tries to access that address, a piece of hardware called the Memory Management Unit, or MMU, steps in. It uses this special map, a page table, to translate that make-believe virtual address into the real physical location in RAM. It happens instantly, and the program is completely oblivious. It's a beautiful illusion. And the benefits of this were just enormous. First off, boom, external fragmentation was completely gone. Any free frame in memory could be used by any page. This meant you could fit way more active programs into memory at the same time. Everything just became simpler and so much more efficient. Paging was a revolutionary way to organize the memory we have. But then, computer scientists, being who they are, asked an even bigger, even crazier question. What if we could just bend reality? Now, that just sounds impossible, right? How can you possibly use more memory than you actually own? Well, this is where the illusion gets even deeper and way more powerful. Welcome to the world of virtual memory. This technique cleverly uses a piece of your slower, but much, much bigger hard drive as a sort of overflow parking lot for your RAM. It creates this enormous imaginary memory space for every single program, making each one feel like it has nearly unlimited RAM, even on a computer with very little. And this diagram shows the relationship perfectly. The program sees this huge, continuous virtual space. The operating system, meanwhile, acts like a master stage magician. It's constantly shuffling the pages the program actually needs right now into the small, super fast physical memory, while leaving everything else sitting out on the hard drive. The secret sauce behind this whole illusion is a principle called demand paging. The system is actually pretty lazy, but in a really smart way. It doesn't bother loading a program's entire set of pages into memory when it starts. Instead, it just waits. It only pulls a page from the hard drive into RAM the very first time the program actually tries to use it. It's like a just-in-time delivery system for your memory. So what happens when the program asks for a page that's not currently in that fast RAM? Well, that triggers an event called a page fault. Now, fault sounds like a bad thing, but it's not really an error. It's more like a signal. It's the program raising its hand and saying, "Hey, operating system, I need a page you've got stored out on the hard drive. Could you go get it for me?" So what if memory is totally full? When that happens, well, the page fault occurs. The OS knows it needs to make room, so it has to choose a victim page to kick out. It uses a page replacement algorithm to decide. One of the simplest ones is called FIFO, first in, first out, which just boots out whichever page has been sitting in memory the longest. That victim page gets saved back to the hard drive, the new page gets loaded into the now empty spot, the map gets updated, and the program carries on, completely unaware of the frantic little swap that just happened behind the scenes. This whole system of virtual memory is an absolutely incredible feat of engineering. It honestly feels like magic. But like any good magic trick, there's a cost. And when the illusion starts to break, the performance of your system can just fall off a cliff. Just think about it for a second. That swap we just talked about, it takes time. Your hard drive is thousands of times slower than your RAM. So if your system is so low on memory that it has to constantly swap pages back and forth, just to keep running, it ends up spending all its time managing memory and almost no time actually getting work done. And that condition has a name: thrashing. This graph shows it perfectly. As you add more and more programs, your CPU utilization goes up, which is great. But then you hit a tipping point. There's not enough physical memory, the system starts swapping constantly, and bam, CPU utilization completely collapses. Your computer is working harder than ever, but it's achieving nothing. It's the ultimate state of busy work. So, from the messy problem of fragmentation to the elegant solution of paging, and then finally to the grand illusion of virtual memory, we've seen how these clever ideas let our computers juggle the impossible. Our entire digital world is built on this foundation, which really just leaves you with one final thought. What's the next great illusion going to be? What's the next trick that will redefine what our machines are capable of?